Hi, we are Team Inspiration, a diverse and now international team consisting of middle and high school students. My name is Ish, and I'm the Deputy Team Captain and Electrical Lead of Team Inspiration. This video will cover the aspects regarding the strategy and design behind the whole of our latest AUV, Onyx.
Hi, my name's Colin, and I'm the Mechanical Lead.
Hi, my name is Noah, and I'm on the Mechanical Sub-Team.
Hi, I'm Mabel, and I'm the Technical Paper Lead.
This year, we focused on achieving and perfecting all the capabilities planned for our previous AUV, Gray, while also designing our new and improved AUV, Onyx. We realized it was just as important to finish Gray because just as our first sub, Orange, taught us valuable lessons, Gray has taught us even more.
From the completion of Gray, we realized the value of sturdy components, weight balancing,
Simplicity, and most importantly,
modularity. Every year, the team needs to construct a platform to connect and maneuver the sensors and payloads to the mission objectives so that they are able to interact with the game elements to score points. Our whole design strategy is to make our AUVs as maintainable, reliable, and modular as possible so that our program can work to its fullest capability.
Similar to our previous two subs, Onyx features a dual enclosure design, one for our electronics and the other for our battery. Our main enclosure is an 8-inch diameter and now has an increased length of 18 inches from the previous 12 inches. The increased length allows for more freedom in electronics placement without compromising maintainability or structural integrity.
to ensure effective waterproofing of the enclosures, we used a 2 O-ring system provided by Blue Robotics. This ensures that if one of the O-rings is compromised, the other can still hold the watertight seal. Also, with 2 O-rings, we have more friction against the inside of the enclosure, meaning that a full sub flood is less likely to happen.
Our hull is configured using a standard 8-motor hexagonal configuration. The thruster placement allows for movement in all 3 directional axes, surge, sway, and heave, and all the rotational axes of pitch, yaw, and roll. By using this configuration, we are able to adjust for any center of mass imbalances.
The whole of our AUV is designed to allow sensors or payloads to be placed in a variety of configurations based off their optimal position.
We use several multi-pin connectors that connect the sensors and thrusters to the inside of the enclosure. These are wet connects that are sealed from both the inside and outside of the enclosure plate. The reason why we chose these over simple penetrators is because simple penetrators have the single failure point of weak epoxy.
This year, we also completely revamped the interior of the enclosure. Based on the server slot system, the multi-layer design and PCB backplane allow for easy maintainability and troubleshooting. The PCB backplane also allows us to remove generic components such as USB hubs and Ethernet switches and localize them directly within it. On top of that, we also don't have to deal with the countless wires filling up the enclosure plate to plate. Our team prioritizes systems thinking when it comes to the design of the AUV. Our competition strategy incorporates requirements, detailed design, and testing to create our sub. Before even creating initial designs of our AUV, we started by completing several trade studies to determine which features would fit our requirements best. We analyzed subjects ranging from the overall frame design and material selection all the way to the low-level fabrication methods. With the moved up competition deadline, we realized the importance of planning all these initial decisions earlier on in the season.
The 3 requirements that we prioritized the most this year were simplicity, maintainability, and modularity. The ultimate benefit of these requirements is the ability to troubleshoot and the ability to expand for the future. The discreteness of these different parts through these requirements is important to ensuring the functionality of the sub at all times and getting back on track when things do fail.
Upon the completion of our initial planning and decision making, we created detailed CAD models, prototypes, and proof of concepts to see our design and evaluate its feasibility. This is one of the most important parts of our design process as it gives us a basis for the fabrication of the entire sub in the future.
Using project management values, we emphasize the analysis of various parts of the project with the identifiers of schedule, cost, performance, and risk. Schedule being the time and labor needed, cost being the monetary cost, performance being the component successfully functioning when integrated into the subsystem or system, and risk being the downsides and potential failures. Regarding the design process of the whole, there were 3 main sections that we focused on: the frame, the mounts, and the enclosure.
Our frame is constructed out of 80-20 aluminum extrusion, a build system known for its cost efficiency, simplicity, and modularity. While it isn't as fancy as other options such as CNC or water jet cut parts, it provides the sturdy structure our AUV requires. This takes advantage of schedule, as well as other options will take a lot more time to produce, while 80/20 can be adjusted to our designs quickly in-house. The disadvantage of 80/20 is its blatant lack of hydrodynamics. The reason why we still choose to use 80/20 is because in competition environment, we do not need to move quickly, so we do not need to be extremely hydrodynamic to keep the robot stable when moving.
The mounts for the thrusters and enclosures are a combination of laser-cut Delrin and MJF printed clamps. The Delrin provides stability for the thrusters due to its strength and directional integrity. The clamps, designed with large surface area and enhanced with friction with DISM, prevent the enclosures from slipping or rolling out of position.
Our sensor and small payload mounts are created using standard FDM 3D printing technologies, designed and manufactured in-house. This allows for quick prototyping and troubleshooting of custom components without waiting long lead times for new parts and mounts.
The enclosure clamps are designed with maintenance and simplicity in mind. Each clamp is divided into 4 pieces and secured to each other using stainless steel screws. This way, if a portion of the clamp becomes damaged, we only have to replace that bit and not the entire piece. The small size of each piece also allows us to print the entire piece on a standard 3D printer for our temporary emergency replacements.
This competition strategy is undoubtedly one of the most effective ways our team has been able to handle tasks and complete them. As you can see, with this strategy, we were able to create an AUV that fulfilled all of our forefront requirements and create a streamlined process to help us understand our own tasks.
The development of the AUV can be described as failing fast so that we can reach a better design quicker. The way we did this is by iterating in CAD so many times and verifying the designs by 3D printing them that when it came to finalizing the design, little or no tuning was needed. And even if we were to tune it more, we could easily do it due to the modularity of the designs.
At the beginning of the design process for the whole, we use our method of analysis through schedule, cost, performance, and risk to see what materials, layouts, and manufacturing methods we might use. This also entails that we do research on the planned designs. What gives us this is an effective but a simple method to get started on designing. Along with this, we look at our previous designs due to their success. For gray, we're able to take inspiration from orange.
After completing our initial research, we were able to design in CAD, which is where we fail fast to iterate fast. CAD was our main method of creating proof of concepts and prefabrication planning this season, as it was easily accessible, detail-oriented, and effective at speeding up the design process.
Upon completing the CAD, we can present to the team through a preliminary design review. This gives us a chance to get feedback and general pointers from our coaches and fellow team members. When we present our designs in CAD and prototypes, our team can provide critical review from the criteria of performance, such as meeting our requirements, the cost, and the material qualification. The PDR provides a good model for how we produce any product on Team Inspiration.
After finishing all of this, we could now fabricate. Fabrication was done with their manufacturing capabilities and the materials that we decided were going to be best for our sub design. The important part of fabrication was using the correct manufacturing methods and cross-checking them with CAD. With the fabrication finished, we could move on to testing to ensure that the sub works smoothly.
Finally, how our team conducts tests. We strongly believe that to conduct an effective test, a test plan must be written out and understood by all the testers. We perform testing in both virtual and physical environments, using inspection, demonstration, analysis, and test methodologies.
With the virtual environment, that being the CAD software, we're able to perform many quantitative tests. These tests would aid fabrication in how parts of the robot would be assembled. For example, we could look at the center of mass, pattern intersection, or material tests to modify the design. In the center of mass test, the computed and end result helped our designer adjust the denser objects toward the center of the mass more. With the intersection test, we could see where parts were intersecting with one another and needed to be moved. Both of these combined allowed us to create an optimized design in CAD before even moving to the real environment.
Now after the CAD was finished, we needed to build the design. Another example of in-pull testing would be when the motor propellers were not turning in the correct direction and the thrusters were not evenly mounted. Walking through different steps of a plan allowed us to troubleshoot and get the sub moving straight in the end. These sort of qualitative tests were extremely important for us to get the AUV working in water, not just in CAD.
As you can see, our team's methods and strategies of project management, structured design processes, and detailed testing enabled us to create an optimized hull design. We were able to consider the hydrodynamics, buoyancy and weight distribution, propulsion vectors, material, maintainability, simplicity, durability, scalability, schedule, cost, performance, and risk, and also whether our materials will be developed in-house or through external vendors. By using these methods in the coming RoboSub seasons, we hope to continue to create effective AUVs.
To see more about our team's sensor optimization strategy, check out another skills video on our website. We would like to thank all of our coaches and mentors and sponsors for supporting us all throughout this season. See you in 2022.